This next little segment, we're going to have a look at the laws of conservation of energy, which is one of the most significant laws, if not the most significant law in the whole of physics. It really governs everything that happens in the physical world. This idea that energy can't be created or destroyed, it can only be transferred from one place to another or transformed from one type to another. And that really is significant because it underpins an awful lot of physics, not just in mechanics, but in electricity, throughout the quantum world, throughout astronomy, into all different aspects of physics. It's absolutely crucial. And it can be simplified just by saying that whatever event takes place, the energy in equals the energy out. Very crude, but a simple way of looking at the situation. What we're going to do is we're going to have a look at the situation, and we'll use Harvey for this one, with him having a crane. Makes life a lot easier. So we'll say that Harvey has lifted an object, okay, and he has an object in his hook there. And what he does is he drops the object so it falls through a height delta H there. Okay, now if we look at that, we can say that the object before Harvey dropped it had gravitational potential energy relative to the ground of, so that's mgh. Okay, so as it falls, it loses that much gravitational potential energy. The mass of the object multiplied by the gravitational field strength of the field it's in, multiplied by the height it's fallen through. And what that object will do, it will gain kinetic energy as it falls. So it loses gravitational potential energy and it gains kinetic energy, which we've discovered was half times mass times velocity squared. Now, because of the law of conservation of conservation of energy, these two things must be equal to each other. So what we can now say is that mass times gravity times change in height, sorry, not multiplied, will equal half times mass times velocity squared. And what you'll notice here straight away, hopefully, is that mass appears on both sides of the equation, therefore will cancel out. And what that shows us now is if we put that in without the mass and then rearrange it, we're left with that. The velocity of an object that falls depends on only the gravitational field strength and the height at which it fell through. It's independent of mass. It doesn't matter what the object is, it should hit the ground at the same time. Now, if you think back to our video on resistive forces, obviously here we've neglected things like air resistance, friction. So that is why in reality things don't tend to hit the ground at the same time on Earth. But if you did this experiment on the moon, as NASA astronauts famously did on Apollo 15, you got to see that a hammer and a feather dropped from the same height actually hit the ground at the same time at the same speed due to simple conservation of energy laws. Okay, so here we're going to have a look at the situation of a runaway train. So we're going to have Thomas coming in at an initial velocity u, under no engine power. We're just going to say he's a runaway. Okay, so he's coming in with initial velocity u. He travels down the track to the bottom of the hill and goes up at the top. And what we're going to see if we can find out is using conservation of energy, whether we can work out at what speed he arrives at the top of this next hill. Okay, so he starts up there. Now we've got two different heights, h1 and h2, and we've also got, we will assume, a frictionless track, which is a pretty scary concept all round. Okay, but what we are going to consider is the change between here, where Thomas starts, and here where he finishes. So actually these two values, h1 and h2, aren't too important, other than to tell us, if we were to just go across there, what the change in height between those positions is. The intermediate positions aren't too important. What we really want to know is what's the difference in energy here and here. It's a little bit more complicated than what we looked at in the previous example because there's an additional term. He's not got zero kinetic energy to start with. He's starting with a velocity. Okay, so initially Thomas starts at the top with gravitational potential energy compared to the point where he finishes, mg delta h, but he's also got some kinetic energy, which is a half mu squared. And what we're saying is that by the end, that will all have been converted into kinetic energy half mv squared. So we've got an additional term here. Now, just as before, you'll notice that mass appears in every term. So nice and easy, that can disappear. Okay, and we're left with G delta H plus a half U squared equals a half V squared. If we multiply across by 2, we've got 2G delta H plus U squared equals V squared. Now that is something you have seen before. If we look at one of the Suvat equations with V squared in it, well, V squared was equal to U squared plus 2AS. And let's think about this. Well, earlier on we said that in the gravitational potential energy derivation, the change in height was just the displacement, and we know that gravitational field strength is also the acceleration due to gravity. So those two equations are absolutely fundamentally the same thing. Conservation in energy and Suvat, two different ways of dealing with the same problems. You can choose really in the exam which way you want to go about it, which way you feel is more comfortable for you. Okay, so in this clip we'll just change the orientation of things. Instead of looking at things moving through vertical and falling, we're going to have a look at some horizontal motion and just see a slight difference that we have to pay attention to with this. Okay, so we're going to have a look at, say, Devious Diesel here, who's moving along with a nice quick velocity of u, and for some reason, as he's travelling down, needs to hit the brakes, maybe a cow on the line or something like that. Gets down to here, and he's hit the brakes and reduces speed to a velocity v, much safer approaching an unwary cow. So, what we've got to do is consider what are the energy changes in this. Well, over on this side, he's got kinetic energy equal to a half mu squared. Over here, there's kinetic energy, which is a half mv squared. Okay, because v being his final velocity. Now, what's going to have happened there is they are going to be different. And whereas before we said, well, energy has to be conserved, well, it still does here. So the difference in energy has got to be accounted for in some way. Okay, so the difference is equal to the work done by the brakes. So we started with a half mu squared, and we've finished with a half mv squared, but we've also got a factor of work done by the brakes in there, which is force times displacement. Now, what the problem we've got here is we cannot cancel the mass, as we were doing in the vertical examples, and rearrange this to find the braking force or the braking distance if we happen to know the braking force. So we can rearrange this by simply going, well, we've got half mu squared minus half mv squared equal to the work done by the brakes. A key follow-up to this question, of course, is, well, where does that energy go? We've said work is done by the brakes, but it must go somewhere. Energy can't be created or destroyed, so it must turn into something. So in that period of loss of kinetic energy, where's it gone? Well, there's a few places it could have gone. There will be certainly some sound created from the braking, but the most significant thing, and what the sound itself will eventually turn into, of course, is heat due to the friction between the brakes, the wheels and the track itself. And the net effect will be that the brakes, the wheels get hot, and eventually that heat is then transferred to the surroundings to warm them up.